That's great. Okay. So today we'll start with our continued discussion on instructions. Last time we had one program of uh, that one program we did regarding to uh, that exchanging two words, right? That is what the program we had yesterday, right? So today we'll continue on uh, further instructions. Okay. Okay. So one of the instruction I told you is exchange, and I hope you have used exchange to reduce the number of instructions. See, uh, even what happens in your programming, right? It is possible that certain task is given to you. You do competitive programming, right? So you know that in that multiple ways of solutions are possible. One is the naive solution, which may use more memory, more space. Another is the optimized solution. In again, the optimized solution, it can optimize certain thing, like it can optimize time, it can optimize space, or it can optimize both. Or so multiple solution of a problem is possible, and that is what we have seen already in the last lecture. That I can use move instruction to exchange, I can use exchange instruction to exchange, right? And now onwards also, to do a task multiple instructions can be used. That will be our conclusion, and that is of course very understandable, that to do a task it is not necessarily one one method or one way will be there. Okay. And one more thing, that if you will observe that which method is best, that not necessarily defined by one method. That depends on your situation, that depends on your application, that depends on the power available to you. There's just several factors you can decide based on time that is available to you. So we can, it is not like the particular method is suitable. Sometimes both are equal, you can use any one of your choice. Sometimes particular one is suitable, but it doesn't make that method best, because it may not be suitable, but other method is more suitable than this one in the other scenario. Okay. So that is what we will keep in our mind now onwards, and we will continue our discussion on few more things. Okay. So up to exchange we have completed. Now next is load effective address, register and source. What you have to do, you have to load effective address to a register of a source, right? Now effective address is what your offset address. Offset address of a source is stored in register. That is what the meaning is. Okay. Now suppose I am having, if I am defining like n1 dw1234h. So I know that n1 is pointing towards certain location. N1 is a variable. That means it is pointing a memory location. It is pointing an offset, and that offset, if I want in bx, that offset if I want in si, then I'm going to write lea sin. LEA, load effective address of n, load offset of n in bx. Okay. So that is what load effective address is, right? Suppose I want that the content of bx and content of si both are added together. Whatever result comes, that should be taken as memory location, and that memory location's offset is stored in di. Are you getting it? Are you getting this point? What is this? Suppose my my bx has certain value, si has certain value. Addition of those two is taken. Ha. That doubt. So what do you think? Like what it should be? Like, okay, tell me. Suppose it is that 1 2 3 4 is like 1 2 3 4 is bx, right? Si is say great. Address is store or offset. See how address and offset are different, Priyank. How address and offset are Okay, to store, no, wait, Jenil, I'm coming to your point. Jenil, I'm coming to your point. Let me complete the doubt of Priyank. How that address and offset are different? Tell me what is in your mind regarding to offset and address. Suppose this is the content of BX. This is the content of SI. What I have to do, Jenil? This is for you. BX plus SI. So these two are added. So it will become 6. 1, 2, 3, 6 is addition. That should be taken as address. So it is 1, 2, 3, 6 and offset of that. So this memory location's offset, what is that? What is offset of this memory location? Do not hesitate. You know the answer, but you see that why we are doing so. Do not get confused with the points. You know the answer. What is offset of this memory location? What is the offset of this memory location? 1236 is taken as offset of certain locations. The segment address is CS or DS, right? Or that this segment address, I have not changed the segment address. Actually, this location is DS1236, right? Because BX and SI are default that offset of DS segment that we have seen. BX and SI are acting as offset of DS. So this is actually location DS1236. So what is the offset of this location? What is the offset of this location? Do you understand offset? Yes, 1236 is offset, right? 1236 is offset. So that 1236 is loaded in DI. So DI has 1236. Okay, DI has 1236. So you may say, okay, but why can't we just add them and move that value? That is okay. I told you multiple ways are possible. You can also have like addition of this two, and that you can simply move to DI. That is okay. The same thing. This is just addition is stored here. Addition of this two is stored here. That's it. Right? Because what we have taken, see BX, content of BX and content of SI are added. So this is the addition. That is that memory location. Now that memory location is DS, this offset, this memory location. This memory locations offset, that is this itself. That 1236 itself is stored in DI. Understood? Now yes, Priyank, what was your case? How memory address and offset are different? Offset itself, yes, we can say yes, but see, base segment plus offset, that is okay, that is true. But here I have just what is the size of DI? Can I store 5 bits or can I store 16 bits? I cannot store 16 bits. I cannot store 5 hexadecimal digits, right? So this is just a size of 16. So I'm going to store offset only. So address, if you will read somewhere address, they mean offset here. Understood? We will now never be able to store entire physical address ever, because we don't have that much. Any resistance is not of 20 bit size. So we will never be able to store entire address ever, until and unless we are having some specific arrangement, but it is not default architectural arrangement available. Then you have to manage it by software in case you want to store some managing some program, but otherwise by some instruction you will never be able to store, because architecture doesn't support that. Okay, fine. So that is load effective address. Have you studied that offset assembler directive? Have you studied offset assembler directive? that madam will cover in detail, but I will let you know overview of that. Right? What is offset directive? That will also take offset of the that memory location specified. You can write it like, of course, madam is going to take it in detail, but you can write. Suppose I want to do this task, ne? I can do it like move in bx. What to move? Move in bx. What to move? Offset. Offset is assembler directive. It is not instruction of 8086. That is what you have instructed to your assembler. That you have stored offset of n. So offset is assembler directive. Take offset of n and store it in bx. That is what we are doing here. Take offset of n and store it in bx. So these two instructions are equivalent, but this is to 8086 and this is to assembler. Understood? So that is what that is what we are doing here. Okay. So of course, madam will take segment and offset assembler directives, right? One more directive is that segment. What is that? Move bx segment n1. What it will do? What it will do? Can you understand what it will do? This is assembler directive once again. What this will do? What is n1? What is n1? N1 is your variable. Will it? Yes, it is a variable, right? It is your variable. Okay, so it is declared somewhere. Yes, so it is declared like this, right? So it is having its because it is a memory location. N1 is a variable pointing a memory location, right? It is pointing certain memory location, right? It is pointing certain memory location. So it will have its segment address. It will have its segment address. Suppose it is if you have seen in your class, so that will be suppose in the laboratory, if you have seen that it is 0744. This is standard value taken by assembler, and then 0000. This can be the address of n1. So this is offset and this is segment. So segment address of your n1, wherever n1 is defined, that segment address should be copied to bx. Copy segment address of n1 to bx. Understood? Same way we have another directive, that is, as I told you, offset. What is the difference between these two? Offset n1. Instead of this is as it is, this is as it is. Offset n1. What will be stored in bx in this case? If this is the scenario, yes, offset of n1, that is 0000. True. So getting these two. So these are the segment, what you can say, assembler directives. Of course, madam will take in detail. So we should compare. So these two are valid methods for copying offset of n to a register. Okay, now yesterday I think Jenil was asking that how you can bring the value offset of address of n1 into SI. Now are you clear with how to bring address of n1 to SI? Is it clear? Okay. Now next is LAHF. Next is LAHF. Load AH with flag register. What is the size of flag register? What is the size of flag register? 16 bit. What is the size of AH? 8 bit. Okay, load AH. So in AH, you have to load your AH. By what? By flag register. but flag register is of 16 bit, this is of 8 bit, right? So you are going to use lower 8 bits of flag register. So if you will see your flag register here, these lower 8 bits are stored in AH. Okay, lower 8 bits are stored in AH. You may say, okay, why would we like to store a flag register to AH? Why would you like to uh, okay, now tell me, suppose, see, this is why would you like to store? So, suppose you want to check whether in my after my operation, after certain operation, parity flag is 1 or not. What will you do? Suppose I ask you that I have performed some operation X, right? Let me know whether the parity flag has been occurred or not. How will you come to know? So for that you have to know the status of this bit. Yes or no? You have to know status of this bit. So how, to access this bit particularly, of course, we will take that example in few minutes. This example that I want to check status of particular flag. So what I have to do, first of all, I have to extract this from the flag register, and that I am going to use using this instruction. That flag registers 8 bits in that parity flag, auxiliary carry, all the flags will be stored in AH. So last 8 bits are stored in AH. So now I have that in AH, I can process on that. Okay, so we will definitely take that examples based on this. So many programs are possible based on this. Okay, so that is what LAHF is. Now, what about S? Can you tell me what about SAHF? What it will be? Store AH to lower byte of the flag. What it is? What we are doing here? In flag, I am storing. Yes, store into flag register. Store value of AH to flag. Reverse operation. True. So this is 8 bits. So this is what very useful instructions these are. We will take example at that time. It will be more clear. Okay. Uh, because we need few more instruction, and that's why I'm not going for this now. But fine, these two instruction I think are clear to you. Right? See, in data transfer instruction, flags are not affected. When you are just moving data from here to there, flags are not affected. Like move instruction or other instructions are not, which are data transfer instructions in which data is transferred, like LEA. In these instructions, flags are not affected. When it is arithmetic and logical operations, at that time flags get affected. Okay. So few more data transfer instructions are yet there. What are they? Let us quickly see them. Load DS. Load DS. Okay. So what is that? What we have to load, you have to load, this is load DS along with BX kind of thing. So what can be this? What we are storing here? Load whatever the content at location 4326 location, that is loaded to BX. Whatever the content at the location 4326 are loaded to BX. Now BX, that means it. So can you tell me which memory locations are now copied to BX? Whatever it is, like 4326, 4326. That is copied to BL or BH. Yes, 4326 and 27 is copied to, yes, 4326 and 27. What is 43? Kevin? Yes, it is BL. This will be in BL and this will be in. Are you clear with the cable? This will be in BH. It is 4326. Okay, you have written it in the reverse way. Okay, I understood. I just was worried that you are not clear. Understood. That is okay. 4326 and 27. Okay, so now your pointer is pointing at which location? Currently your pointer is pointing at which location? 2, 8. These two are used, these two are copied. Currently you are pointing at 2, 8. This 2, 8 and 2, 9 location content is copied to DS, data segment register, DS. So what you are doing? You are not only loading BX but also loading DS. DS is a data segment register. Okay. Same way you can see LDS SI comma N. Can you tell me what will happen here? LDS SI comma N. What will happen here? Yes, it will load SI as well as DS. True. What will be in SI? Address of N or content of N? In SI, what will be there? Address of N or content of N? No, no, content of N. It will be content of N. That is what the point is. See here what we are having. Content of this location, content of this location is copied here. Understood? It is not load effective address. Don't get confused with this two. Okay, it is not load effective address, it is load using this address. Okay, so whatever is stored at N is copied to SI. Then after two locations, whatever is available that is loaded, that data is loaded to DS. Understood? So make it very clear here. This is what load ES, like DS. Now you don't load DS. Instead, you load ES, extra segment register. That's it. So at this location, whatever the content is, load it to BX, and next location that is point incremented by 2 should be loaded to ES. Okay. What is this? BX content should be taken as address. BX content should be taken as address. At that address, whatever the content is should be copied to DI. Are you getting it? Suppose my BX is 79. Suppose my BX is 789A. So 789A is a, suppose my BX is say 1234. Let us take BX 1234. It is easier to understand. BX has value 1234. So 1234 is taken as address. Content of that address is copied to DI. Okay, the content of that address is copied to DI, and because two locations will be needed and the next location is taken as, so 1234 and 1235 locations content in DI, and 1236 is copied to ES. Is it making sense to you? Everyone is following me here? Anyone having any doubt can ask me right now, because very much important things. Otherwise, see, instructions are very simple, but you need to work on them because you might get confused over that. That what is the use, right? So otherwise it is not difficult. Okay, they are not difficult. 1234, yes, it is one content of BX is should be taken as address. Why? Why 1234? Because 1234 is the value of BX. Value of BX in square bracket. That is, it should be taken as address, right? So that address, yes, it is indirect one. It is indirect one. This is indirect mode. No, not BC. LES, no, see what here it is compulsory to copy word. You don't have you don't have option of using one. I mean, you cannot load B. See, actually, what is the use? If you will observe, na, ES is a whenever this is actually DS and BX is used, DS and SI is used. When this is used, whenever you want to jump to certain location, so whenever suppose I am at the current location, but I want to go to certain DS and certain SI location. I want to go to, currently I am working on certain data segment 1, and its offset is suppose certain offset 1. Suppose I am working over this, but now I want to take data from this data segment 2 and offset 2. So data of this is stored where? This should be stored in SI. Currently this should be stored in my DS. So at that time this instruction is useful. So at that time you will generally use it to copy entire 16 bit. Understood? uh, 7 8 9A is 7. See, these two are different instructions. This is instruction 1, this is instruction 2. Now Ansh, can you can you tell me your question? I'm not clear with your question here. 7 8 9A is pointer. That means, I mean, I'm not clear with your question. Can you elaborate? See, 7 is indirect is what? This is actually you are directly specifying the address here, right? It is not AH. It is, this is 7 8 9A hexadecimal, right? So this is the direct address you have provided here. This is indirect. So content of BX is taken as address. That's why it is indirect. Getting the point? What is indirect? I'm not specifying the address there. Understood? If I'm providing address, then it is a direct mode. No? Is it clear, Ansh? Now, should I move, or are you? If you have doubt, we can clear. But hope it is clear to you. Is it clear? So fetching address from register is indirect. That is, this one is indirect. No? Okay. So are you okay? Now let us go to the arithmetic. So data transfer instructions are over. Now we are going for arithmetic instructions. Add instruction you have already studied. Add that you have already used in the laboratory, right? We will of course cover it quickly. What is that? Destination and source, right? Your what it is? Your destination can be a register or memory location, right? Source, what about source? Source can be immediate number, register, or a memory location, right? So you can add immediate data as a source, you can use register, and you can use memory location. Both of them together cannot be memory locations. Memory to memory addition, memory to memory movement is not allowed. Okay. So so this you have already studied. Which are the flags that are affected? All the flags are affected here. Okay. And this different modes, I think, like immediate data, 8-bit addition, 16-bit addition, indirect addition. I think this can you understand this? Content of SI is taken as address. That address address of that content pointed by SI is added to BX. Okay. So this is what that that offset of price, this offset of prices and offset of the content of BX is added, and that is taken as addition. And one more thing, what is ADC? This instruction you studied in 8085. What is ADC? This is the same as you studied in 8085. Add with carry. And you know the use of add with carry? What is the use of add with carry? Anyone? 16-bit addition by ALBL when you want to add greater. Yes, Kaushal, you are true. You are correct here. But what is the case like what, but here we are having option of adding 16 bit, right? So if you will do addition of 16 bit by I mean if you will that will be easy for us. Yes, that for our case it will be 32 bit. Yes, so Janil and Dev, yes, and Kaushal, I think yes, you are also clear, so good. So that is the use of ADC. So I'm not covering that because we have so many other interesting program. What is X here? It is a memory location variable. Okay, so your destination can be a register or a memory location. What do you understand by that? Register or a memory location. Yes, it is allowed. Your destination can be a register or a memory location. Okay. That what about subtract? Subtract and subtract with borrow, right? So again, all the flags are affected. You can subtract 16 bit, you can subtract 8 bits, you can subtract immediate data, you can subtract in direct mode, you can subtract in other addressing modes as well, right? This you have studied. And mostly we are not going to use this type of modes, we will just use indirect and direct mode mostly, until and unless we need some higher level programs. But initially we are not going to study this type of modes. But yes, they are, you should be aware of this type of modes are available. Okay. So I'm skipping this, not skipping rather, I should say, I'm going quickly through this because these are very basic instruction. Already you have utilized them a lot in 8085. Do you need any discussion over this? If you need, see, they are variables. You, as you say, X and N1. So they have taken like prices and table. These are just variables. Okay. They are just variables. Huh. SBB is same as ADC because you, if you want to go, if you want to subtract with borrow, right? So not only that application, so many other applications we are going to study about this, right? But yes, it is like subtract with borrow. Next is increment. Next is increment instruction. What is increment instruction? What it does? What was that in 8086? It was not INC. What was it? INR, if I'm not wrong. In 8086, it was INR. Yes, increment register by 1. Yes. And in 8085, it was INR. INX and INR. Okay. So here it is INC, increment destination. Yes, INX was also there. True. Okay, so you can increment your not only you can increment your variable as well, not only the register. See, this is a variable. Temporary is a variable, like data segment in the temp is defined as word or something, right? So you can increment not only 8 bit, not only 16 bit registers. You can also increment your memory location pointed by variable, or also you can increment certain location pointed by your like index registers even, or any other register even. So what is this? Can you understand what is this? You know, this byte pointer we have taken yesterday. Can you understand this instruction? What is, so suppose my content of bx is there 1 2 3 4. Bx has the value 1 2 3 4. What will be this? What will this will point to? 1 2 3 4 is taken as content or address, first of all? Yes, it is taken as address. Byte pointed by 1 2 3 4. Yes, it is. So actually, it is increment of 8 bits only. So and this is actually word pointed by location 1 2 3 4. Right? Yes, true. Which are the flags affected? All these flags except the carry flag. Carry flag is not affected. All other flags are affected. Okay. Now, what is next? Decrement instruction. So again, the same thing. You can decrement not only the register. Of course, register example is not given, but of course you can write it like DEC, BX, CX, whatever you want to write. DEC, AX, anything is fine, right? And memory location and this, anything is okay. This all are same. All flags are affected except CF. Decrement by 1, subtract 1. Okay. It can be register or a memory location. Destination can be a register or memory location. Sample program to add two numbers. Just to observe, can you understand this? This I think you have already gone through. Do you understand this? Let me know if it is. Are you clear? If you are clear with. In case any discussion is needed, we can discuss.
Congratulations.
Observe. I will give you few more and some other programs to deal with. This is very basic one. If you understand, let me know. We can go to the next one. If it is clear, let me know.
ಅಲ್ಲ ಒತ್ತು ಸ್ವಲ್ಪ ಇತ್ತು ಐಪಿನು
Okay, Priyank is clear with this. What about other status? Do you understand
Hello.
this program? Okay, Janil, Yash, Abhishek. What about others? Are you clear with? Yash is clear. Janil is clear. Kunal is clear. Okay, so all of you, I think majority of you be clear. That is their choice, and that they want to add two 8-bit numbers, right? They want to add two 8-bit numbers, and they want to use. In case here, what is assumed that yes, here it should be AL. Yes, that is a good question. This should be
Okay.
here AL and BL. Otherwise, what will happen? BH
અવાજ નહીં આવતો
and BL. Sorry,
હા બોલ
BH, or rather, what I have to do?
બોલ
If I want to use this one, then what I have to do? 1, 2 more instructions are needed here. Yes, of course. Thank you, Sanish. That will be true. What is the case? Two values are taken in an AL and BL, right? And I have added AX and BX. But if I want 8-bit addition, I should actually write AL BL here, right? But if I'm writing like this, then what will happen? AH is already containing this AH from this, so it is not going to give me the correct result. What I have to do? If I want to use this instruction anyway, what I have to do? Move AH 0 0. Move AH. I am changing AH, na? BH 0 0 H. If I am adding like this, then I am using this instruction, will not be problem now. Is it okay? Or otherwise, what you can do, you can directly copy this to AX, but AX will not permit it. So, no, that you cannot do. But yes, you can do up to this. Otherwise, you better you write here AL and BL. So that is what is true. That is what the problem was. True. Now we are going for the next case. That is CBW. CBW. That is convert signed byte to signed word. What it will do? The sign, suppose in whatever the byte is stored in AL, sign bit of that is MSB of AL, is copied to AH. Suppose my AL is MSB of AL is 0, then entire AH is 0. If MSB of AL is 1, then AH is FF. Yes, value of addition will get stored to AL if I am writing ALBL. Vanish. ALBL, then AL, otherwise AXBX, then in AX, in source. So are you clear with what it will do? That MSB of the byte is copied. Why we will need? We will take that in certain cases, but right now this instruction is given to us. We will use certain applications. When it will be needed, I will let you know, as I will let you know about LAHF, SHF. Right? Convert word to sign double word. Word to double word. So what will happen here? Can you understand by logic what it will do? Word is there and you want to convert it into double word. How will you do that? I mean, what it will do here? Sign bit of the given word that is stored in AX. In AX, you are going to store a word, and sign bit of that is MSB of that, is copied to DX. Okay, so now if you will observe that as a DX and AX, what is the size of DX AX together? If I will see it as, what will be the size of DX AX if I see as a single register? 32 bit. So yes, so this word is converted to this entire double word. I mean, you can, certain instruction will use this DSAX as a word, right? So we will need it when we will study those instruction. We will need this, right? But right now, what you have to learn, that word is stored in AX, MSB of that is taken, and that is copied to DX. Entire DX will have the value that sign bit of this is having. This is useful in certain instructions, and at that time we are taking DX and AX as a whole double word. That instructions are taking so, right? This both instructions are not affecting any flag. Make sure that which flags are affected by which instruction, right? Okay. Next is negative. Ha. Yes, that all ones. DX is having FFFF. No flags are affected by both the instructions. Negate instruction, what it will do? Negate instruction is obtaining two's complement of the word, or I mean whatever the destination is. Destination can be register or memory location of 8 bit or 16 bit. Okay, so it can be like 8 bit data stored in register, 16 bit data stored in register, 16 bit pointer, or 8 bit pointer, but it will take two's complement of the data. Whatever is in AL, two's complement is taken, stored in AL, right? So that is what is negate instruction is. Okay, so this is just negative, two's complement we are finding. This is the extra feature that we have obtained compared to 8085, right? Next instruction is multiplication. This is what I was telling you, that multiplication instruction is available in 8086 for getting multiplication. What you were doing, um, you were yes, you were doing multiple additions, you were performing, right? Here we are having multiplication instruction. Now suppose I am multiplying two 8-bit data. What can be the result, size of the result? Two 8-bit data is multiplied. What can be the size of the result? 16 bit. So no, 8-bit data, Ronak, I'm talking about 8-bit data. Suppose two bytes are multiplied, then result can be a word. It may go up to word, right? So so what it is, so what will happen, like suppose you are multiplying AL with source. See, multiplication will, so see, multiplication and source, only that is the method, like MULBH, MULCX. Only one operand you are specifying. Other operand is fixed in A register, accumulator. It can be in AL, it can be in AX. One is fixed in AL and AX, right? If it is 8-bit, then AL. If it is 16-bit, then AX, right? Another operand you need to specify by providing the source here. Another operand you will specify by providing the source here. Now, if it is the provided source, your provided source is of 8-bit, here you will say it is 8-bit, then it is AL into BH and stored, that result is stored in AX, right? And suppose it is your source specified is 16-bit. If both are, so then what will be taken as another operand? Will it take AL or AX as another operand? If specified source is of 16-bit, another operand will be AL or AX. Yes, it will be AX. The another operand will be AX. What will be the result? What will be the result? I mean, it will be 32-bit. Where to store 32-bit? Do we have any resistance of 32-bit? Do we have any? Yes, we don't have any register of 32-bit. So what we will take? We will use DX and AX. I told you just a few minutes back that DX and AX is used as single register together, right? So what AX will store out of that 32-bit, lower 16-byte or higher 16-byte? What AX will store? Lower 16-byte or higher 16-byte? Lower 16-byte. And DX will store most significant higher 16 bytes. Okay, and if you will observe it as a whole, then DX AX will, as a whole, it will show you 32-bit result. Okay, and here if it is 16-bit, then if it is result is 16-bit, then what AH will store? What AH will store? Higher 8 bits, and what AL will store? Lower 8 bits. Okay, fine. Whenever the result goes in AH here, that means your addition, that means your multiplication goes to 16-bit multiplication in the case of 8 into 8. And if your multiplication goes to 32-bit, that means DX stores something. It is non-zero value because of this operation. Then what will happen? Um, um, then your carry flag and overflow flag will be one together. Okay, that means suppose I perform some operation, right? And my result, if it is of 16-bit, then if the result goes in DX, if my DX is updated because of mul instruction, then CF and OF together will be 1. So I will check if CF and OF are 1, then and only then DX contains the result of my multiplication. Okay, otherwise my CF and OF, if DX is not updated, possibly my multiplication is, though it is of 16-bit, but it is covered in AX itself. I don't need to go to DX. I no need to update DX. Result is covered in 16-bit itself, right? Then CF and OF will be 0. Same way, if 8 into 8 is covered in 8 bits, AH is not updated because of mul instruction, then CF and OF is 0. If it is updated, AH is updated because of mul instruction, then CF and OF will be 1. So this CF and OF is updated, these flags are updated if the result is stored here. They are not updated in the usual manner. CF is 1 doesn't mean the carry has occurred. CF and OF both are 1s, that it means that DX has, that means this multiplication has resulted into 32-bit multiplication. Okay, but what about other flags? They are not defined for this instruction. Other flags are not defined. They are not updated because of this instruction. Okay, they will not show you the values because of mul instruction. Only these two flags are updated. They are also not showing their usual results. Okay, so this will be unchanged or undefined for this. So is it making sense to you? Any doubt in case, please ask here. So what are the options that we have here? See, what we can do, that we can move one operand to, what you can say, in suppose I want to perform 16 into 8. What to do? 16 bit operand into 8 bit operand. How to write that program? If it is 16 bit and 16 bit, suppose it is 16 cross 16. So this I will store in AX, this I will store in CX. Okay. Here what I will do? Also, I will suppose I am storing this in AX. Suppose I am storing this in AX. Right? Can I store this in CL? Yes or no? Is it possible to store this in CL? 8-bit data, can I store in CL? Suppose my N1 is DW, pointing this. N2 is DB, pointing this. Yes, CL is data and CH should be 00. Okay. Okay, so first question, can CL store this N2? Is it capable enough to store N2? Yes. Do I have any instruction that will copy N2 to CL? Do I have any instruction that will copy N2 to CL? Yes, move instruction itself will do that. Na? Move instruction, what will be that move instruction? What will be the move instruction? Yes, move CL comma N2. Move CL comma N2. True. Move CL comma N2. So CL. Now can I write MUL CL? Can I write like this MUL CL? Or should I write MUL CX? Why I cannot write MUL CL? It is permitted, na? My source can be 8-bit data. What will be the trouble if I am using MUL CL? What will be the issue? Yes, then it will be 8-bit multiplication. Yes, then it will perform 8-bit multiplication. So it will perform actually not AX and CL. It will perform AL and CL. So I have to write MUL CX. But I have stored this in CL. So what I have to do with CH? If I am not modifying CH, then it will take its random value of CH. Yes, so I have to make it 0. And that is what we have taken here. This program is for that. Is it clear, everyone? Mul instruction is clear to you? Okay. Now, IML instruction we will complete, and what is that? It is same as that multiplication, but here it is considering that my operands here are signed numbers. Okay, so it will perform, the result will be like signed multiplication, like two negative numbers are taken, then result should be positive. And if two positive numbers are there, then result should be positive. One positive, one negative number, result should be negative. So here operand, so you are considering the range from, suppose it is 8-bit, you are not considering range from 0 to 256 or 255. You are considering the range of minus 128 to plus 127, right? So otherwise it is same, like, but just the thing is that your operand specified are signed numbers, right? Same way that if the result goes to 32-bit number, then BX is modified, then CF and OF will be 1, CF and OF will be 0 if 32-bit result is, I mean, most significant bit or most significant byte or most significant word is not changed, then this 2 will be 0. Other are undefined for that. The only difference will be the multiplication will be considering your numbers as a signed numbers. That's it. Okay, so sign will be considered here using imul. Okay. Next is division instruction and IDIV instruction, but of course we are running out of time, so that will be covered in the next lecture. Division instruction, and then onwards we will go for the logical instructions and some programs. So in the next lecture, we will consider some programs for the practice. So this instruction, please revise them. I'm not going to revise them again because based on this instruction, I'm going to give you few programs in the next lecture. So revise them and we will discuss few more instructions in the next lecture. Any doubts so far? Okay, so we will meet in the next lecture now.